Oh, welcome everyone. I'm Niels. I work for Hugging Face as a scientist and as an open source developer. Some people maybe know me from the project Sentence Transformers, or so sometimes called SentenceBird, SBird. In the past 3 years, I've been working extensively on the topic of sentence embeddings, how to train them, how to tune them, how to use them in different scenarios. And at Hugging Face, we're organizing in July the Flax JAX community event. So the Flax JAX community event, that's a new deep learning framework similar to PyTorch or TensorFlow developed by Google. And a nice advantage of JAX Flax is that it works well with TPUs and that you can use the advantages of TPUs quite easily. And to spread the awareness of JAX Flax and to spread the awareness of TPU from Google, we partnered up with Google Cloud and Google AI. They are providing free resources to TPUs. And we want to use the Flax JAX framework to develop different applications. And in this project, we're focusing on sentence embeddings. So first of all, how can you use transformers for sentence embeddings? The approach is quite easy. So you take the input sentence, how to learn Python, for example, you pass it through BERT, and BERT gives you contextualized word embeddings. And then based on these contextualized word embeddings, you have some pooling operation. For example, this can be a mean pooling, that you take the mean of all the word embeddings. And this gives you some fixed size sentence embeddings. So if you take standard BERT, you have 768 dimensional output vector. Out of the box, this does not perform well. So if you just take standard BERT based uncase, you get rather poor sentence embeddings. Because in a vector space, what's important is that all dimensions contribute equally and that all dimensions need to have the same scale, because we want to use them for some unsupervised tasks and we cannot learn based on the output of BERT. So what we need is to do some fine-tuning on some data. The best approach to do fine-tuning is the multiple negative ranking loss. So in this presentation, I will extensively talk about the multiple negative ranking loss, covering all the details about this loss, because it's, I would say, the best loss function to train sentence embedding models. It's quite flexible. It's really nice properties you can have for training data. So it's really easy to get a lot of training data for this loss. And it also works really well. The naming is not consistent. So I call it multiple negative ranking loss. In other papers, people just call it training with in-batch negatives. In computer vision, people call it often info NCE loss, or sometimes you also see this NTX and loss. So the naming can be quite different. So as training data for this loss, you need to have positive pairs. So you have some anchor and some positive pair. It can be quite diverse which type of training data you use. This can be, for example, a query or a question and the answer. It can be a question and the duplicate question, for example, in some online communities. Or from scientific paper, you can take the paper title and and another paper title it's citing. So you take the BERT paper title and you take the attention is all you need and have this pairs, or you can also do the BERT abstract and attention is all you need paper abstract. So there are a lot of different variations what you can use as training data. What you want is that this pair anchor and P should be close in vector space. So you want to have the query close to the answer in the vector space, or you want to have the question with the duplicate question close in the vector space, or you want this one paper title and the paper it's citing close in the vector space. And what you want is that if you randomly select pairs, so you take some query and some answer, different answer, for example, then you should want to have it far away in the vector space. So the intuition is here that it's unlikely if you take randomly a question and randomly a passage, randomly an answer paragraph, it's unlikely that the paragraph will give the answer to the question. So it's safe to assume that if you select randomly to a pair, that they should be far away in the vector space. So what you do for this loss is you embed the anchor in the vector space, and then you embed the different positives of your batch. So here we have a batch size 5 in the vector space. And you want to move the matching positive here, the P1, close to A1. And you want to push away all other P's far away in the vector space. So A1, P1 should be close, and A1 to P2 to P5 should be far away in the vector space. So in papers, you sometimes find this mathematical definition. What we do is we optimize a cross-entropy loss where we take some similarity between AI and PI, and you normalize it over all the similarities of AI, PJ. I will give in a second like a more intuitive explanation. So currently it sounds a bit difficult, the loss, but I think it's really easy to understand this loss. And as similarity function, we're flexible what we want to use as similarity function. Most common selection for similarity function is the cosine-similarity between two vectors, or the dot product between two vectors. So here's a more intuitive explanation for this loss. So we have a question-answer data set. So we have some question, how many people live in Berlin? And then we have the answer to this, around 3.5 million people live in Berlin. And we have different other answers in our batch. So the second answer is Washington, D.C. is the capital of the US, and the 2021 Olympics are held in Japan. These are the different answers we also have in our mini batch. So what we do is we compute the text embeddings and we compute the similarities. So we check what is the similarity between A1 and P1, which is, for example, 0.5, between A1 and P2, which is, for example, 0.3, and between A1 and P3, which is 0.1, for example. And then we see it just as a classification task. So it's really similar to a simple pairwise classification task. So we have the prediction of our model, which is 0.5, 0.3, and 0.1. And then we say, okay, our gold label is 100. So this is the correct answer to our question. And then we just use simple cross-entropy loss. So it's a simple classification problem. So you have a question, you have 3 possible answers. Which of the 3 answers is the correct answer? So in a mini batch, you have these pairs. So you have these answers and these question and these answer pairs. So the first question is, for example, how many people live in Berlin? Answer around 3.5 million people. Second question is, what is the capital of the US? The answer, Washington, D.C. is the capital. And third question, what are the Olympics this year? And then the answer is 2021 Olympics are held in Japan. So what you do is you compute the similarity between all these embeddings. So you take every sentence, you embed them in the vector space using the transformer network. Then you compute the similarity. For example, you can use the dot product where you just take the vector for all the A's and the vectors for all the B's. And then you get like a big matrix where you have here the similarity of A1 with all the P's, and here the similarity of A2 with all the P's. And then you do a cross entropy loss. So our gold label is where we have the ones on the diagonal. So for the first question, the first answer is correct. For the second question, the second answer is correct. And for the third question, the third answer is correct. And it's quite easy to implement. So here we have some PyTorch code from sentence transformers where we embed first all the questions in our vector space and then all the answers in our vector space. We multiply it by some similarity function, add some scaling. I will explain the scaling on the next step. And then we have the labels. And here we just set the labels as a list of scores, like a list where we know, okay, for the first question, the first answer is correct. For the second question, the second answer is correct. For the third question, the third answer is correct. And then we just call from PyTorch cross entropy loss between the scores and the labels. So it's basically just 3 lines of codes you need to implement this loss function. So this is currently in PyTorch. For the community event, we would need to have such a version in JAX. So one critical component of this loss is how to compute the similarity of A and B. So A and B, just a reminder, are vectors or sentence embeddings. And there are different options how you can compute the similarity. One option is to compute the dot product. So you multiply vector A times vector B. Different option is to use cosine similarity. So cosine similarity, you multiply vector A and vector B, and you divide it over the length of A and the length of B. However, if you train with cosine similarity, it does not work well because the score differences are quite small. So if you have if the correct answer has a similarity of 0.9 and different answer might have this cosine similarity of 0.5, this is rather small difference for cross entropy loss. So what people use is scaled cosine similarity. This is basically to compute cosine similarity and you add some scaling factor. So it's really easy to compute. So scaling factor, a common scaling factor that works well is, for example, 20. So you take all the cosine similarities. In this matrix here, you have all the cosine similarities, and you just multiply it by 20. This will make the differences larger. So if you have small difference in cosine similarity, if you multiply it by 20, you get a larger difference, and cross entropy loss works better. Of course, you can also do scaled dot product, where you take the dot product and you scale it by some factor. This can be interesting when the dot product is limited in length. So if you have vectors which are of unit length, which are of length 1, then the dot product is equal to the cosine similarity. So the dot product the max score for the dot product can just be 1. So and then in this case, you would also need to train with scaled dot product. So there's one optimization we can take if we train with cosine similarity. So the optimized network structure looks the following. So we have our text, we pass it to BERT to get contextualized word embeddings. Then we have our standard pooling operation where we can, for example, take a mean pooling to get a fixed sentence embedding. And then we can apply a normalization on top of that, so that sentence embeddings, we get sentence embeddings with length 1. In that case, cosine similarity becomes simply the dot product. A nice thing, if you have a network structure which outputs sentence embeddings of unit length, of length 1, is that the Euclidean distance is proportional to cosine similarity. So for example, if someone wants to use your sentence embedding for clustering using k-means, k-means uses Euclidean distance, and Euclidean distance would not work well if your embeddings are not normalized. And by normalization, Euclidean distance is proportional to cosine similarity. So k-means it will be using cosine similarity. So you do not have a break in the similarity function you train the network on and the similarity function you use for clustering. If you use such a network which outputs normalized embeddings, so where every sentence embedding has a length 1, you have to use the scaled dot product for training. Otherwise, you have the same issue that the differences in scores are not too big. The question is what should you train with? Should you train with cosine similarity or should you train with dot product? So far, there's not a lot of evidence in literature. Some papers use cosine similarity, some papers use dot product, and there's not really good motivation for the one or the other, and it's also not clear which one is better. So for cosine similarity, we know the vector has the highest similarity to itself. So if you take the cosine similarity of A and A, it's always 1. So the highest similarity to a question would be the question itself. For dot product, this property does not hold. There can be other vectors which lead to a higher dot product. So the dot product of A and A could be smaller than the dot product of A and B, which could make sense for question answering. So if you input a question, you do not want to retrieve the same question from the vector space, but you want to retrieve the answer from the vector space. With cosine-similarity and normalized vectors, it's equal to dot product. So we know that the vector length is 1. And when we normalize the vectors, it's also proportional to Euclidean distance. So it works well with k-means clustering. So that's the advantages of cosine-similarity. For dot product, disadvantage can be that it might be slower with certain approximate nearest neighbor methods. So some approximate nearest neighbor methods, so if you want to do search over a large vector space, they require that you know the maximal vector length, but for dot product, for unnormalized vectors, you do not know the maximal vector length. And then you have to do some complex operations to transform your vectors to a normalized vector space, which is quite complicated. So in summary, it can be slower and harder to use with certain approximate nearest neighbor methods. And if you train with dot product, it does not work with k-means clustering. So k-means clustering is not compatible with dot product. So in a paper we presented this year, we analyzed cosine-similarity and dot product for the task of search. So you input some query and you want to retrieve some document providing the answer. And there we notice quite a difference depending if you train with cosine-similarity or if you train with dot product. So what we notice is that dot product retrieves longer passages. So what we see here is the number the system returns, like the number of characters the system returns. And then we see the distribution of the hits for different queries. And for the track COVID dataset, we saw that a lot of really short answers were retrieved. And due to a special property of this dataset, but also for other datasets, we saw that cosine-similarity models prefer to retrieve short passages for search, while dot product models prefer longer passages. So the explanation for this is that for cosine-similarity, the length of the vectors is always the same. It's always 1. So it does not matter if you encode like a short text or a long text with a cosine-similarity model, the length is always 1. For dot product, however, what the model can encode is the length information in this vector. So a longer passage, a longer document can lead to a longer vector, which then can result in a higher dot product. So there are different papers which propose modification to the scaled cosine-similarity, but it's not clear how good these modifications are. So they often do not provide the motivation and do not do an ablation study on that. So if we do the scaled cosine-similarity, we have some scaling factor C and we multiply it with standard cosine-similarity. First question arises like how to choose the scale C. So this is still unclear. In literature, you find common values between 14 and 20, but there's like no systematic study on that. What is the optimal scale factor? But the scaling factor can have like a really big impact. If you select scale C equal to 1, it will perform really badly. If you choose like also a really large scaling factor, it also performs quite badly. In the Convert paper from PolyAI, where they trained on a lot of Reddit data, a Convert model, sentence embedding models specifically for conversational AI, they increased the scaling while they were training. So they start at a scaling factor of 1, and then they increase it up to 23 over the first 10K training steps. So they increase it step by step. In the CLIP paper from OpenAI, they set C as a learnable parameter. So they initialize so that the exponential of C is equal to 20 and keep this as a parameter which can be learned while training. So the network updates this parameter. But this is rather clear, or the impact is rather unclear. So it's not known if it will make a difference. Will it lead to better results? Will it be faster in training? And it's also unclear if the modification depends on the data and the task. So for some data sets, maybe a small scaling factor is good. For other data sets, maybe a large scaling factor is good. So there's still a lot of question marks how to choose the scaling factor, even such it can have quite a big impact. So another modification proposed by the CLIP paper and also other papers is to use a symmetric multiple negative ranking loss. So far, we took the question and compared it to all the answers, but we can also do the opposite direction. So given the answer, what was the question? And this is quite easy to compute. You take the loss between answer and positives, and then you compute also, you swap the two. So you take the loss between positive and an anchor, and you would divide it by 2. Here again, the impact is unclear if it will improve the performance or will lead to faster training times. So it could be interesting also as part of this community week to do some experiments on that and to find like a scientific answer to it, like how do you select the scale and should you use symmetric or non-symmetric multiple negative ranking loss. Different modification to this loss was presented by Google in 2019 and 2020. What they do is they add a margin. So what they want is that there's like a larger margin between the different classes. So for example, in the original embedding space, it's fine if we have like this different clusters which are quite close to each other. But what they want is to have like a larger margin between this cluster so that they are better separated in the vector space. So they modify the similarity function. So for the positive pairs, they subtract some margins. So they take cosine-similarity and then they subtract 0.3 for the positive pairs. So if the answer and if the question and the paragraph has a cosine-similarity of 0.9, they subtract it by 0.3. So in your computation, they have just a similarity of 0.7. And this will force that the question and the answer is closer in vector space. Again, the impact of the margin, or in the paper, they showed that it works well when you do a multilingual training, where you train with translation pairs. So you have an English sentence and a Chinese sentence, for example, and you want to have them close in the vector space. But the impact of the margin is unclear for other tasks and data sets. So it could be a modification that is helpful, but it could also harm the training for other tasks and data sets. So now I will come to how to improve the quality of the embedding model. The simple trick is to train with larger batch sizes. So the task, when you increase the batch size, becomes more difficult and the results get better. So here we see a paper from Baidu, Rocket QA paper from Baidu. And then the black line is like a simple training setup. And by just increasing the batch size from 128 to like 4K, 8K, you increase the quality significantly of the model. It's quite easy to understand. So assume you have some query given and you have 10 different passages provided, which is the answer. So it's quite easy to identify the correct answer out of this 10 passages. However, if you have a query given and you have like 1,000 passages provided, it's a lot harder to find the correct answer out of these 1K passages. The other option that works well to improve performances is to train with hard negatives, which is the red line here. So we see the performance with hard negatives is a lot better than training without hard negatives. So what is hard negative? Previously, we trained with these positive pairs. So we had some anchor and we had some positive. Now we train with triplets. So we have an anchor, we have a positive, and we have a hard negative. And the hard negative should be similar to the positive, but it should not match with the anchor. So, and this is quite tricky to set up right. So for example, a bad example would be you have the anchor, the question, how many people live in London? And the positive would be around 9 million people live in London. And then by some process, you get a hard negative, or you get the negative as London has a population of 9 million people. If your triplets look like this, this will confuse the model because it tries to put A and P close in vector space, but A and N far away in the vector space, even such that N is like completely fine answer to find answer to the question. So it's really important to have good hard negatives. So a good hard negative would be, for example, around 1 million people live in Birmingham, second to London. So here, this text is also talking about London. It's talking about how many people live somewhere in England, but it does not provide the answer to the question, how many people live in London. So this would be actually a good example. And getting this triplets right is not so easy because it can be quite easy that you include a lot of bad examples, bad negatives, which will then harm your training performance. So how can you find hard negatives? There are two strategies you can do. First is to exploit some structure in your data. So for example, if you work with a citation graph of scientific papers, you can, the title of a paper, then you can take the paper, some cited paper. So the BERT paper is citing the attention is all you need paper. And then from that attention is all you need, you take some paper which is not cited by the BERT paper and add it as a hard negative with the intuition that BERT and attention is all you need paper is closer in vector space or should be more similar than some paper which is cited by attention is all you need, but not cited by the BERT paper. Another way to set it up would be if you think about like Stack Overflow, we have some question, we have the answer, which has like a lot of stars, which is like really good. And then you take some answer, which has few stars from the same question. And you assume, okay, this answer is like better for the question than the answer, which has a few stars. Another strategy is to mine hard negative. So for example, if you have in your training data just question and answer, you take, for example, BM25 to find the top 100 most similar pairs to either the anchor or the positive, and then you select these randomly. But you have to make sure that these are actually negative. So for example, if BM25 gives you like such a text, this would be not considered as a negative. And this, if you have too many of these in your training setup, it will actually harm the performance. A different way to improve the quality is to train with better batches. So for example, one training set which is working really well is Stack Exchange. So in Stack Exchange, you have like 140 different subforums. So there's a subforum of Stack Overflow everyone is familiar with. But there's also like a subforum on travel, on cooking. And assume you have now all the data sets, all the questions, and all the answers from all Stack Exchanges. Naive approach would be that you do randomly sample from all pairs. So in your batch, you have a question on Python with the answer for this Python question. You have a question for visa and traveling with the answer for this visa traveling problem. And from cooking, you have some question how to cook pasta with the answer how to cook pasta. And here finding the right answer for a given question is quite easy. I mean, you have the question for Python, and then in the batch, you just have to look for the one programming answer in the batch. So it will not identify what is the specific answer to this specific Python question, but just check the batch, what is one programming answer. A better approach would be that you, for example, that you sample pairs from one subforum. So you take one subforum. So for example, you select Stack Overflow, and then in your batch, you just have questions from Stack Overflow. You have a question from Python, a question from Java, a question from C with the respective answers. And now the model must not only identify, okay, this is a programming question, but must identify, okay, this is a programming question about Python. So an even better approach would be in Stack Overflow, you take questions which have similar tags. So for example, you take Stack Overflow and the Python tag, and then you include 3 questions which have the Python tag. So one question about Python, NumPy, and pandas. And now the model will learn to differentiate between fine-grained programming questions from Stack Overflow. It might be if you train with such a setup that you also want to add random batches. So if you do the separation of the batches from Stack Overflow and traveling and cooking, or even maybe on a tag level, it can be that, for example, that the Stack Overflow vector space could overlap with the travel vector space. So the model never learned to differentiate programming questions from travel questions. So one way would be that you train, for example, with 90% difficult batches. So in 90% of the cases, you take one of these difficult batches. And for 10% of the cases, you take one of the easy batches where you take questions and answers from all stack exchanges. Or you could also do, you could start with mainly random batches. And then when the training progresses, you'll train with more and more difficult batches. So yes, so training is quite easy with this setup. So the loss is quite easy to define, quite easy to implement. So the magic is in your training data. So what type of training data do you have? How do you get, for example, hard negatives? This can be have a big impact. And how do you maybe can exploit some data to get better batches for the training? So these are like two factors, really important factors to tune the performance of your models. So in the Flax JAX community event, TPU will be provided by Google Cloud. So I'm not super familiar with TPUs, so far mainly use GPUs, but there's one important difference between TPU and GPU. So a TPU creates a graph for your of your training steps. So when you send some operation to a TPU, it first creates a graph, the computation graph. This computation graph is then optimized and built. And this optimization and build step is quite slow. So the first step is quite slow, but the result, the graph, is cached. This has big difference to training with PyTorch on GPU. So training with PyTorch on GPU, the graph can be dynamic. So you can, for example, train with batches of different lengths, or where you do padding of different lengths. However, here for the TPU, every computation, every step you do must be the same. So you cannot differentiate why you compute, what to compute. So one way is to pad all your text to the same length, or you can also use different padding lengths. So if you have like a batch where the input is just 10 tokens, it would not necessarily make sense to pad it to the full length of like 512, but you can maybe use different padding lengths like 64, 128, 196 to 56. And then you pad to whatever the next number is available. And this would create like 4 different graphs on the TPU, which are cached and used. So now we come to training data. So for training, so there are three things how to improve the quality. One is simply increasing the batch size. The larger the batch size, usually the better the performance. The second is to use better batches, maybe also using hard negatives. And the third simple way to improve sentence embedding models is to train on more data and more diverse data. So I did, as part of my research, did create like a standard training setup where I trained a model for 2000 steps with a batch size of 256. And I evaluated a lot of different data sets. So here you see some or the top ranking data sets on the performance. So the performance is evaluated over 14 different tasks from different domains. And what we see, which works really well, are these question answer data sets. So for example, here's a small data set from Stack Exchange, just 300,000 examples where we take the title and the body from Stack Exchange, where we train it and we get like really good performance. Then the GUAQ dataset from LNII, they mined question answer pairs from Google Autosuggest, also get a really good performance. The MS Macro is queries from Bing with the answer passage and a hard negative passage, also gets really good. And then we have Yahoo Answers getting good questions. And then slowly when we go down, we see that the performance drops. So quite commonly people in sentence embeddings, they train on NLI and on SNLI and multi-NLI, but this performs rather not so good. So it's not really bad, but also not great because it's really narrow in the domain and not working that well. So in conclusion, what works well are these question-answer pairs. And this could also maybe be interesting for other languages. So for English, we have a lot of data sets available, but for other languages, it's harder to get some suitable data. But however, there might be a lot of communities. I don't know, maybe in Korean, there's some big Korean community where people ask questions, providing a title and a body, or providing a title, the question, and the answer. And this could maybe mined and be used to train a Korean-specific sentence embedding model. So which model worked well? So this is based on personal experience. So my favorite model is MPNet, which was presented by Microsoft, which is sadly not yet available in Flax JAX. And then different models which also work well is Roberta, BERT, and then when you go to smaller models, Distill Roberta, Tiny BERT, Distill BERT, and then at the bottom we see Albert. And multilingual models, MBERT and XLMR Roberta also work well, but sadly XLMR Roberta is not yet available in Flax. First of all, when you read these papers, for example, on Albert or on Electra, people compare, or the authors compared on the GLUE dataset, but sadly there's no correlation. So for example, the Electra model works really well for classification tasks and really works well on the GLUE and SuperGLUE dataset, but it produces really bad sentence embeddings. So don't be fooled by, okay, I take whatever is the best model on GLUE, SuperGLUE, and train it for sentence embeddings, so there's no correlation. And I can recommend to stick, for example, with the Roberta model or like the Distill Roberta model. They perform quite well. So training on more data is quite important, but if you train on multiple data sets, how do you deal with data sets of different sizes? For example, we have one data set, network questions, which are queries from Google with answers from Wikipedia, where we have 100,000 data pairs. And then we have a data set maybe from Reddit with comment and response, where we have 600 million and more data pairs. So option one is to do equal sampling from all data sets. So train 50% with NQ and 50% with Reddit. You can also do some scaling with some temperature. So that you train with network questions more than you would expect from just 100K data pairs, and fewer on Reddit. So this is quite common in neural machine translation. Or there's an option to define a max data size. So you say, okay, everything above 1 million, I kept everything above 1 million. So for Reddit, you assume that the size is just 1 million. So you train, and NQ has a data set size of 100K. So you train roughly 10% with NQ and 90% with Reddit. What could also be interesting is to add batches across data sets, so that you take some pairs from your Reddit dataset and some pairs from network questions dataset, so that these two datasets do not overlap, and not map to the same vector space. So finally, there was quite a lot of interest on multilingual models. So the best way to train multilingual models would to have suitable training data in your languages. So for example, you have some question-answer pairs in your specific language, but so far it's rather hard to get it compared to English. Another way is to train with a translation bridging task. So you have some English data, for example, question and answer, and you have some parallel data from machine translation, so an English sentence and a German sentence. And you can train with this translation pair also in this multiple negative ranking loss. And then you train alternating on your English data and on your parallel data. And this was, for example, used for the multilingual universal sentence encoder. A different way I proposed is the multilingual knowledge distillation. So you have your English teacher model, which you trained on whatever data set you want. And now you want to make this model multilingual. So what you take is some parallel data, like here an English sentence and German sentence. you send the English sentence to the teacher model to get the sentence vector for the teacher. And then you send the English sentence and the German sentence to your multilingual student model, which produces 2 sentence embeddings. And you ensure that the English sentence embedding from the student model and the German sentence embedding from the student model are close to the English sentence vector from the teacher. And this will align the vector spaces. So the German sentences and the English sentences will be mapped to the same vector space, and they will have the same structure as the vector space from the teacher model. The advantage of this multilingual knowledge distillation is that it's easy to extend models later for more languages. So once you have the English model, you can just easily extend to whatever language you want. The training setup is also easier. You can focus on good English model and then make it multilingual, and works on the general text domain as good or better as alternative approaches. It has some limitations or disadvantages. So it ignores some country and language specific properties. So people from Japan ask different questions than people from US. So in US, in the data sets, you see a lot of questions, how to do taxes in the US, but I doubt that people from Japan will ask specific question, how can I do my taxes or US taxes. To learn this country language specific properties, authentic training pairs from the language would be required. So it will not work if you translate any data sets, but you would need authentic questions and answers, for example, from Japanese, to get these country and language specific properties. So the timeline of the community event is the following. So there will be some talks from today until beginning of July, which Patrick will announce later, about JAX and Flax, about TPU and computer vision and NLP. So hopefully we get some basic understanding what is JAX and Flax and how to train on TPU. And then from July 7th to July 14th, you will get access to Google Cloud and will get access, or the teams will get access to a free TPU. And then on 15th, the access to the TPU is deactivated, and on 16th, demo should be submitted. So what are the next steps? Join the Discord server. So I shared a Discord server link which we will use for the communication. Then there's a spreadsheet. So spreadsheet with information about the team. So it would be great if everyone could add the name here in the spreadsheet. There are different sub-teams I will come to in a minute. We have a overview of different data sets where you can download it. Also where we try to collect all suitable data sets. There is a tab for new data sets, which are interested, which people can try to collect and provide. And there's some guideline how to provide a new data set. And finally, there's like some open tasks. So for example, we need a train script for Flax and JAX producing these models. We need some optimal parameters for multiple negative ranking laws. As I showed, there are like different options you can use. We would also need a project name. So